You want them, the stranger they become?
Definitely happens.
Well, today we're diving into one of those. It's about that famous double-slit experiment.
Ah, yes. A classic.
Specifically what actually happens, like right at the moment, a tiny particle goes through one of the slits.
Right. Seems straightforward.
You'd think. But the sources we're looking at today, wow. They dig deep into the physics, and they show a quantum reality we're just going through is, well, it's mind-blowing.
It really is. A gateway to the weirdness.
So our mission, let's say, is to unpack that moment, go beyond the textbook pictures, and see what quantum mechanics really says.
Absolutely. What seems mundane at our scale becomes fundamentally bizarre down there. These excerpts take us right into it, from before the slit to, well, some pretty profound stuff about reality.
Okay, let's start there then. Before the particle even gets near the barrier with the slits, our sources mention the wavefunction a lot.
Yes, crucial concept.
For those of us not doing quantum math daily, what's the main thing to grasp about the particle state right then?
Okay, so the key ideas are the wavefunction and superposition. Before any measurement, you can't say the particle is right here or right there.
Not like a tiny ball bearing.
Exactly, not like that. The wave function describes all the places it could be found with different probabilities. It's more like a cloud of possibilities.
A probability cloud. Okay.
It exists in this blurry state, multiple potential locations at once. That's superposition. It's totally different from our everyday experience where, your keys are either on the table or they're not.
So it hasn't, picked a slit it's heading for yet?
Nope, no predefined path. That whole idea breaks down. It's just this spread out probability wave described mathematically.
All right, so this probability cloud bumps into the barrier. What happens right at that boundary, at the slit itself?
Okay, this is where it gets really interesting. The slit isn't just a hole, it's a boundary condition. It interacts with and shapes that wave function.
How so?
Well, two main things happen, depending on the setup. First, diffraction. Like water waves spreading out when they go through a narrow gap. The probability wave does something similar. It spreads out after passing the slit.
Okay. And the second thing?
The second depends on whether we're watching. If you put detectors there to see which slit the particle uses, that active measurement forces the wave function to, well, collapse. The blurriness disappears and the particle suddenly is at one slit or the other. It seems to pick a definite path.
But if we don't put detectors there, if we don't look,
then the superposition continues. The probability wave effectively goes through both slits.
Whoa, okay, hold on. The possibility goes through both slits at the same time? That's still...
Wow.
Yeah, wild.
It is wild. But this simultaneous passage, the superposition, is absolutely essential for the next step, interference.
Right, the famous pattern on the screen.
Exactly. If there's no measurement at the slits, the parts of the wave function that came through each slit start to interact, to overlap.
Like ripples interfering in a pond.
Precisely like that. And this creates that pattern of bright and dark bands on the detector screen. High probability areas, low probability areas. It's like the particle somehow knew about both slits.
Okay, so without looking, it's a wave, goes through both, the probabilities interfere.
Yeah.
But physically, the moment it's at the slit barrier, does it split? Does part go through one, part through the other? How does that work?
That's where our classical intuition just completely fails us and why it's so weird.
Yeah.
The sources stress that describing the passage without measurement in classical terms is basically impossible. What happens is the wave function itself reshapes due to the slits. It gets constrained, it spreads out. Components of this wave do go through both openings.
Components of the wave.
Right. The interference pattern later is the direct consequence. It's not like the particle physically splits in two. It's that the probability of finding it later is shaped by both paths being available. Think about the pond ripples again. The water itself doesn't split, but the wave pattern changes because of the obstacles.
So the probability is what goes for both.
Right.
And those probabilities then add up or cancel out.
Exactly. Add up or cancel out. And that leads us to the big difference. Measurement versus no measurement.
Right.
If you measure at the slits, boom, wave function collapses. The particle behaves like a particle, takes one path, no interference pattern, just two clumps behind the slits like throwing pebbles.
Okay.
But if you don't measure, the wave function evolves like a wave through both slits.
Oh.
And you get that interference pattern, wave-like behavior.
So our measurement fundamentally changes the reality of what happened.
It seems that way. It's like the particle behaves differently depending on whether it knows it's being watched. It's profound.
And there's math behind this, right?
Yeah.
The sources mention the Schrödinger equation.
Yes. The Schrödinger equation governs how the wave function evolves smoothly over time. if you're not measuring. It lets those probability waves spread and interfere.
Measurement.
Measurement is different. It's a sudden, abrupt change, the collapse. The wave function snaps to a single state associated with one slit. It's not the particle choosing, it's the interaction with the detector forcing a definite outcome.
And these aren't just simple probabilities adding up, right? The amplitudes matter.
Crucial point. These aren't just chances like flipping a coin. Probability amplitudes can be positive or negative or even complex numbers. When they combine from the two slits, they can add up constructive interference, making the probability high there, or they can cancel out destructive interference, making the probability 0. That's where the dark bands come from.
Okay.
That cancellation is the smoking gun for superposition, for going through both slits somehow. Measurement destroys that possibility, and you just get simple addition of probabilities like the two clumps of pebbles.
Right, like sound waves canceling out.
Exactly like that.
Okay, now, one of our sources throws a real curveball. The delayed choice experiment. What on earth is that about? Sounds like sci-fi.
It kind of feels like it. Delayed choice pushes the weirdness even further. The basic idea is, what if you decide whether to measure which slit the particle went through after it's already passed the slits?
Wait, after? How can that change anything?
Well, incredibly, the results show that it does. If you set up your detectors later to see which path information, you get particle behavior, no interference.
Even though it already went through?
Yes. But if you set up your detectors later to not see which path, maybe to see the interference instead, you get the interference pattern, wave behavior.
So deciding now seems to affect how it behaved back then.
That's the mind-bending part. It really challenges our normal sense of cause and effect, of time flowing one way.
Yeah, no kidding. It's like the future changes the past.
Well, the most common way to think about it isn't literal time travel. It's more that the quantum state, the superposition, remains undecided, undefined, until the final measurement is made. Our choice, whenever we make it, defines the reality we observe for the whole process. The properties weren't fixed back at the slits.
Okay. That's still hard to wrap my head around.
It is for everyone. It highlights just how central measurement is.
Our sources also talk quite a bit about something called decoherence. What's that? How does the real world mess things up?
Decoherence is absolutely key to understanding why we don't see this quantum weirdness everywhere in our big, messy world.
Right.
It's the process where a quantum system, like our particle, loses its quantum properties, its superposition, its ability to interfere because it interacts with its environment.
Ow, like bumping into air molecules.
Exactly. Even tiny, seemingly insignificant interactions, a stray photon, a vibration, an air molecule, anything that can carry away information about the particle state, even subtly.
So the environment is kind of measuring it without us meaning to.
That's a great way to put it. The particle gets entangled with its surroundings. It leaves little traces, little bits of information leak out. This entanglement effectively destroys the delicate superposition.
And makes it behave like a classical particle.
Precisely. It loses its quantumness and starts acting like a well-defined object with a single path. That's why observing interference in labs is hard. You need incredible isolation.
So the pure quantum stuff is like a perfect scenario. Shielded from everything.
Pretty much. The passage through the slit isn't just particle meets barrier, it's particle state meets environment at the barrier. That superposition is incredibly fragile.
Which brings us back to that really basic question from the sources. What does it actually mean for the particle to pass through then, if it's not just a little ball going through a hole?
Yeah, that's the philosophical heart of it, isn't it? If it's unmeasured, the wave function acts as if it takes multiple paths. The interference proves that.
But if measured, it only takes one.
Right. So did it really take one path all along and the measurement just revealed it? Or did the measurement somehow create the path? Or is path even the right word?
So what are the alternatives?
Yeah. Some sources suggest thinking about it differently. Maybe passage is more like a quantum computation, or a collapse of probabilities. Or maybe, as Bohr might say, you can't really talk about what it's doing when you're not measuring it. The reality is defined by the measurement.
So it's about information.
Ultimately, yeah. Many interpretations lean towards viewing passage as a transition in quantum information, not just a change in location.
Okay. Now, things get even more advanced in some of these texts. Quantum field theory comes up. How does that change the picture of passing through the slit?
Right. So QFT takes it another level deeper. Instead of particles being fundamental little docks, they're seen as excitations, like ripples, in underlying quantum fields that fill all of space.
Like an electron field, a photon
Well,
field.
exactly. So the particle isn't an object in the field, it is a ripple of the field. When this field excitation encounters the slit, the slit's physical structure acts as a boundary condition on the field. It forces the field excitation, the wave function, to reshape itself, like how the shape of a drum skin affects the vibrations.
Okay, so the field itself interacts with the barrier.
Precisely. And there could even be more subtle effects, interactions with the quantum vacuum near the slit edges, things like the Casimir effect, maybe slightly altering the energy. So passage is a dynamic change in the field excitation probabilities.
And what about Feynman's path integral idea? That sounds totally different again.
It's a fascinating perspective. Feynman said, forget about a path. To find the probability of a particle going from A to B, you have to consider every single possible path it could take.
Every path, even ridiculously curvy ones.
Every single one. Each path gets assigned a value, a probability amplitude, based on something called its action.
Okay.
And the final probability comes from summing up the amplitudes for all those paths. Interference just naturally falls out of these paths, can reinforce or cancel each other.
So how does the slit fit in?
The slit essentially filters which paths contribute significantly. Paths that hit the barrier don't count. Paths going through the slits do, and the sum includes paths going through both slits if unmeasured.
And measurement collapses this sum.
Kind of. Measurement makes it so only paths consistent with going through one specific slit contribute significantly. So no single path is chosen without measurement. It's a superposition in all possible histories.
We also kept coming back to decoherence in the advanced sections. Its role seems critical.
Absolutely vital. It's the bridge between quantum and classical. Any entanglement with the environment, however small, kills the coherence needed for interference.
Making the wave function collapse early.
Effectively, yes. It leaks the which path information out, even if we don't detect it directly. That's why minimizing decoherence is paramount for quantum experiments. The passage itself is always threatened by it.
And delayed choice also reappears, still messing with our heads about time.
Yes, Wheeler's experiments really drive home that the nature of the event at the slit wave or particle passage seems bound up with the final measurement choice whenever it's made.
Quantum information again.
Exactly. It suggests the information isn't localized at the slit until measurement. It hints at non-locality and this retroactive definition of the event.
Which leads to thinking of the slit as an information boundary.
Yeah. It's a powerful way to frame it, not just physical, but a place where quantum information is processed. Without observation, the which slit info is delocalized in the superposition. Observation filters it, collapses it.
That fits with things like quantum erasure, too.
Yes, and relational quantum mechanics, where properties only exist relative to an observer or measurement context. Passage becomes dependent on how you ask the question.
Okay, revisiting the quantum field view again, but deeper. The excitations and boundary conditions.
Right, emphasizing again that it's the field excitation interacting with the slit boundary. This forces a reshaping, almost like changing modes in a waveguide. And those subtle vacuum effects, Casimir-like forces near the edges, could play a tiny role too. It's a field transformation.
And non-locality again. The state being spread out.
Yes, the quantum state isn't just at one point before measurement. It extends across the possibilities, across both slits in a sense, until the final detection pins it down. That future measurement's influence reinforces this non-local aspect. The moment of passage isn't classically fixed.
And decoherence and entanglement, revisited one more time. The fragility.
Super important. The purity of the quantum state matters hugely as it approaches the slit. Any environmental entanglement causes decoherence, leaks information, forces collapse. The density matrix formalism helps quantify this loss of purity. The slit is like a sensitive detector for coherence.
Path integral. Again, the sum of history is modulated by the slit.
Exactly. All paths contribute, weighted by their action. The slit geometry shapes which actions are allowed, how the amplitudes combine. Interference is the net result of all these possibilities interacting with the boundary. Passage isn't picking a path, it's the sum interacting with the constraint.
So finally, bringing it all together, the slit as a quantum information transition point.
That really seems to capture the essence from these deeper dives. It's where superposition integrity is tested, where environment and vacuum interact, where wave function components are modified, shaping the future. Passage is fundamentally a transition in the quantum state's information, influenced by measurement, environment, and maybe even future choices.
Wow. Okay, so wrapping up this very deep dive, it's incredibly clear that just a particle passing through a slit is, well, it's ridiculously complicated. It drags us right into the core strangeness of quantum mechanics, superposition, wave functions changing, and this huge, almost unbelievable impact of just looking, of measurement, and the environment.
Definitely. The main takeaway has to be that passing through in the quantum world isn't like a marble rolling through an opening. It's more like a shift in information, a collapse of possibilities that were all somehow present until we force an answer.
It really does make you stop and think, doesn't it? How much our active observation, the information we get, seems to define reality itself, especially with things like delayed choice. What does it even mean for something to happen if it only seems to take definite shape when we look? It's, yeah, something profound to mull over.
Absolutely. A question that keeps physicists and philosophers busy and hopefully gives everyone listening something deep to think about, too.